In this section, we're going to take a look at some antiderivatives. This hopefully is a refresher from what you have learned in previous courses. So this section, we're going to look at some basics of how to do antiderivatives, and hopefully it's a refresher on things you've already seen. So the big idea here is that when I'm doing an antiderivative, I am reversing a derivative. If you don't know what a derivative is, then go back to Calc 1 and look at those types of things. But let's assume we have the derivative of a function as 2x plus 3. What could that original function be? Well, it turns out if we had set the original function to x squared plus 3x, then using the basic common derivative techniques, the derivative of f would have been 2x plus 3. Remember, with polynomials, when you take a derivative, the exponent comes out in front and then lowers by 1. So the 2 would come out in front. We'd get x to the first, 2x to the first. 1 comes out in front, multiplies by 3. 3 times x to the 0 is the same thing as 3 times 1. So x squared plus 3x has derivative 2x plus 3. However, you'll notice that if I take x squared plus 3x plus 5 and take the derivative of that, because the constant 5 has derivative which is 0, it will also give a derivative which is 2x plus 3. And likewise, x squared plus 3x minus 7 also has derivative of 2x plus 3 because any constant has derivative of 0 if it's a constant term. So there's actually a lot of functions that work. However, all of those functions have the same kind of format except with different constants. All of those functions are going to look like some version of x squared plus 3x plus c, where c is a constant. Now, this gets me to the idea of the antiderivative. If I start with a function, an antiderivative of that function, we'll call it lowercase f function, is another function, we'll call it uppercase f function, such that when I take the derivative of uppercase f, I get lowercase f. So an antiderivative is any one of the functions whose derivative gives you the lowercase f. We saw that there were infinitely many. So one way to categorize all of the antiderivatives, or one way to find all of the antiderivatives, is to do what we call an indefinite integral. The indefinite integral of lowercase f is the set of all antiderivatives of lowercase f. And we denote it by the integration symbol, which looks like an elongated s of lowercase f dx. That dx is a differential. It tells us that we are integrating with respect to variable x. This is the entire class of antiderivatives. And the indefinite integral will always be equal to an antiderivative plus an arbitrary value of c. And in this class, we always make C uppercase. That's the typical way to do it. So we can find the the indefinite integral by finding one antiderivative and then tacking on a plus C at the end. So again, hopefully this section is review. And so we're going to use what we know about derivatives to find the indefinite integral of x to the fourth plus 3x with respect to x. So if I want to find the antiderivative for this, what I can do is I can think about what sort of value, what sort of term, when I take the derivative, will give me 4x to the, or excuse me, not 4x, will give me x to the fourth. So I know that when I take the derivative of a polynomial function, that's going to lower by 1. So I need to start with an x to the fifth. And I'm going to have a coefficient of 1 over 5 so that when I multiply the 5 by 1/5, I get a coefficient of 1 in front of the x to the fourth. And then that'll give me x to the fourth, or 1x to the fourth. In a similar way, I say, what do I need to take a derivative of to get x? Well, I need to use x squared. And then what coefficient, when I multiply it by 2, is going to give me a 3? And that's going to be 3/2. So 1/5 x to the fifth plus 3/2 x squared would be an antiderivative. If I want to find the set of all antiderivatives, I simply tack on a plus C. And that would be my final answer. 1/5 x to the fifth plus 3/2 x squared plus C. What about this example? Let's try to find the indefinite integral of 4x plus cosine of x with respect to x. Now, I'm going to start saying finding the indefinite integral. I'm just going to say integrate, because when I say integrate, that's going to imply I'm finding an indefinite or later a definite integral. So we want to integrate 4x plus cosine of x with respect to x. Now, in a similar way, when I integrate 4x, I'm going to raise the exponent on x by 1. And then in order to get a 4 as my coefficient, I need to use a 2. Because, again, that exponent of 2 will, when I take a derivative, come out and multiply in front. Now with cosine of x, that component, it turns out that the derivative of sine is cosine. Therefore, the antiderivative, or one antiderivative of cosine, is sine. So derivative of sine of x with respect to x is going to be cosine of x. The antiderivative, or an antiderivative of cosine of x, is sine of x. And then, as always, I tack on my plus c at the end to give the full class of antiderivatives and not just one specific antiderivative. Oftentimes, linguistically in this class, I will say, oh, the antiderivative. Know that when I'm talking about the antiderivative, I'll misuse the term instead of saying the antiderivative. Instead of saying an antiderivative, I will misuse the term and say the antiderivative. So that is just how we do that sometimes. Now, utilizing those concepts, the idea that antiderivatives are the reverse of derivatives, we can get some rules for integration. These are going to be analogous to our rules for differentiation, that is taking a derivative, but just in the opposite direction. So for instance, if we want to integrate a constant times a function with respect to x, we can pull that constant out front and say that's going to be the same as the constant times the integration of that function. If we want to add two functions together and integrate the sum, then we can actually integrate each function individually. In fact, we did that on our first two examples. We basically said we integrated the x to the fourth. We looked at that first, and then we used 3x. We did the same thing here in example 2, that if we're adding two different functions, I can essentially integrate this one and integrate this one separately, and then tack on a plus c. The other rule on this slide says if you integrate 0, you get any constant that you want. So integrate 0, you get any constant that you want, because the derivative of any constant is 0. So other rules for integration, well, if we're dealing with a polynomial type function, if we have anything which is a term that is x to the nth power, if I want to find the antiderivative of that, what I can do is I can raise the power by 1. So take x to the n plus 1 power, and then take the coefficient. Now here it was 1, and divide it by n plus 1. That's what we were doing here with x to the fourth. We said, oh, that's going to be x to the fifth times 1/5 out front. When we did that here, we did x squared times 3/2 out front. Now that works, that technique works as long as n is not -1, because when n is -1, then our denominator is 0, and that doesn't work. Now, when n is -1, then x to the -1 is the same thing as 1 over x. And it turns out when you integrate 1 over x, you get the natural log of x plus c. Technically, you get the natural log of the absolute value of x, because in natural log, you can't plug in anything that's negative. So you get the natural log of the absolute value of x. Oftentimes, you'll see that in this class, when I write it, I'll write parentheses instead of absolute values. And in this class, when you're writing answers in Moodle, if it's natural log of something, you can just write natural log and then put the argument in parentheses instead of putting the argument in absolute values. But we get natural log of x, and obviously you have to tack on a plus c. That is what you do when n is equal to -1, because when n is equal to -1, x to the -1 is 1 over x. Other rules that you've probably seen before, when I take e to a linear power, e to the a times x, where e is our base e, that's the numerical value associated with natural growth, which is about 2.71828. So I take base e to the number times x, and I integrate that with respect to x. I get e to the ax times 1 over a. Now notice that when a is 1, that's just saying e to the x integrates to give me e to the x plus c. So when a is 1, we get that the derivative, the antiderivative of e to the x is e to the x plus c. If you take any other base other than e, then you have to adjust it by utilizing a natural log. So base to a power, let's just say base to the power x, integrated with respect to x, gives you that base to the x power times 1 over the natural log of b. And then obviously tack on your plus c. With trig functions, the rules for integration work in the reverse way that our rules for derivatives work. So the derivative of sine is cosine. Therefore, the antiderivative of cosine is sine x, and then obviously tack on a plus c to find the indefinite integral. So when we integrate cosine, we get sine of x plus c. Now the derivative of cosine is negative sine. So if we're starting out with a positive sign and we want to integrate that, we integrate sine and we get negative cosine plus c. So if you go from integration, you integrate cosine, you get a positive sine. You integrate sine, you get a negative cosine, obviously plus c. Now the derivative of tangent is secant squared. So if you integrate secant squared, you get tangent plus c. Other trig things that you may know, derivative of secant is secant times tangent. So when you integrate secant of x times tangent of x with respect to x, you get secant x plus c. Derivative of cosecant is negative cosecant cotangent. So if I integrate positive cosecant cotangent, I get negative cosecant plus c. And in a similar way, cotangent has derivative negative cosecant squared. Therefore, if I integrate positive cosecant squared, I get negative cotangent plus c. So let's use those rules and evaluate some indefinite integrals. And like I said, I'm going to start utilizing words in a non-super specific way. Oftentimes I'll refer to things, the indefinite integral, as the antiderivative instead of an antiderivative. I'll also, just say integrate, and I'll use some language interchangeably because they're also closely related. But let's evaluate these two integrals. Always remember that you can pause the video and do all of those kinds of things. Um, do these problems on your own if you'd like, whenever you'd like. I'm going to go straight through these and I'm going to use the rules. So first couple of rules, obviously, since we have coefficients, x times a power, you can think of doing these integration, doing the integration of 18x squared, then the integration of 8x, then the integration of minus 5, and then I'll tack on a plus c at the very end. So when I integrate 18x squared, I'm going to raise the power by 1. That'll give me x to the third. And then I'm going to divide by 3. 18 divided by 3 is 6, so I get 6x to the third. 8x, I'm going to think of that x as x to the first. raise the power from 1 to a 2, and then divide that coefficient of 8 by a 2, that gives me 4x squared. Any constant, that's like an x to the 0. So raising the power by 1 gives you x to the first. So I get minus 5x to the first. And then at the end, when I'm doing an integration, I always have to tack on that plus c at the end to give me the entire class of antiderivatives. But that's it. 6x to the third plus 4x squared minus 5x plus c. Again, I hope this is fairly easy for you, and I hope this is a review for you. Now, in terms of integrating 7 over x, basically I can pull this 7 out front, and I can rewrite that as 7 times the integration of 1 over x. When I integrate 1 over x, that is the natural log of x. And usually I don't do that operation other than in my head. I just say, oh yeah, that's 7 times 1 over x. So that's going to give me the natural log, excuse me, natural log of x plus c, and then I've multiplied by 7. Now, by the way, you might say, should the 7 be in parentheses around the entirety of the natural log plus c, or should I, so in other words, should I distribute that 7 into the c along with distributing it into the natural log? Well, it turns out I don't need to, because 7 times the natural log of x plus a constant is the same as 7 times the natural log of x plus 7 times a constant. Because if I have a constant number, then 7 times that constant number is still a constant number. So whenever we write our constant, we'll just write it as plus c, and we won't worry about putting any coefficients on it. But there you go, 7 times natural log of x plus c. Notice that I wrote natural log of x, I wrote the x in parentheses rather than absolute value. On Moodle, when you write your answers, you can write that in parentheses, although technically we know we have to plug in positive things. Let's do another few examples. I want you to find these indefinite integrals. So I want you to integrate 4 over x to the third, integrate the square root of x, integrate 4x squared plus 5x minus 6 all over x. Again, if you want to try this on your own, you can pause. I'm just going to go right into and do these. Now, with all of these are 3 that are going to be best done by starting out and rewriting. Now, be careful when you do a rewrite on these. In terms of rewriting, make sure you write the integration symbol when you're just rewriting, and then we drop the integration symbol only after we've found the antiderivative, or when we've computed an antiderivative. So here's a rewrite. 4 over x to the third is not like not in the form that I want it to be in to do an antiderivative. So what I would like to do is I would like to rewrite that as 4x to the negative 3. That's just a rules of exponents rewritten. X to the negative 3 is like 1 over x to the third. And then we're integrating that with respect to x. Now this matches the format that we've been dealing with so far. Raise the polynomial format, raise x to a power, that power raises by 1, and then I divide the coefficient by the new power. So all I would do is I would take x to the negative third and raise it by 1. Now, if I take negative 3 plus 1, that's going to give me a negative 2. Be careful about that. When you add 1 to negative 3, you get a negative 2. And then 4 divided by negative 2 is going to be a negative 2. So that comes from 4 divided by negative 2. That's the only term, so I just tack on a plus c, and I am done. So I get negative 2 times x to the negative 2 power plus c. Now, if you want to rewrite that, you can rewrite that as well as negative 2 over x squared plus c. Either one of these is acceptable for this class. Certain professors don't like negative exponents, but it's fine either way for me. Now, just like this previous one, when I integrate when I integrate square root of x, I'm going to rewrite that as well. We're going to integrate square root of x, and if we use the rules of exponents, my exponent is going to be 1/2 or 0.5, whichever you'd like to say. So when I do my integration, now I have the form that I want. I'm going to take the x, and here's what I'm going to do. This is, instead of thinking of this as 1/2, well, it doesn't matter. You can think of it as 1/2 or 0.5, but when I add 1 to the exponent, I get a 1.5 or a 3/2, whichever way you like to put that. If you do 1 divided by the fraction 3/2, you get 2/3. So you get 2/3 x to the 3/2 plus c, or 2/3 x to the 1.5 power plus c. Whichever way you'd like to write that is perfectly fine. Sometimes writing a 3/2 power looks a little bit messy, especially when I'm writing it here, like on this Microsoft Word program. But raise the exponent. The key thing here is x to the third in the denominator can be written as x to the negative 3 in the numerator. Square root of x is the same thing as x to the 1/2 power. And cube root would be x to the 1/3 power. And fourth root would be x to the 1/4 power, and so on and so forth. Now, the last one on this slide was an integration of this rational meaning polynomial divided by polynomial, rational function, excuse me, polynomial divided by polynomial. And on this one, what I can do is I can simply take each term in the numerator and divide it by x. So 4x squared over x is just 4x. 5x over x is plus 5. And then minus 6 over x. Well, that one I can't really divide. I just take minus 6 over x. But notice that when I divided, I made my life a little bit easier because now I have 3 different terms. Each one individually, I know how to deal with. So 4x, we're going to raise the exponent by 1. We get x squared. Divide by 2. 4 divided by 2 is 2. So 2x squared. Constant becomes 5x. And we've seen this before, negative 6 over x. When I take the antiderivative, it gives me -6 natural log of x. Again, I'm putting things in parentheses. If you can also put things in absolute values. Some people are really particular about that. When you write things in Moodle, write them in parentheses. So there we go. That's what we get. 2x squared plus 5x minus 6 times natural log of x, and always tack on our plus c at the end. Let's do a couple more. So let's evaluate these indefinite integrals. Now, the previous couple of examples were all of basically using the tools here and here. So integrating x to a power and then using these rules like the coefficient, dealing with the coefficients, integrating the sum separately, and so on and so forth. Now let's use this tool, and we'll use some trig tools as well. In fact, let's do that. Let's do example 5 and 6 together. So for example 5, we want to integrate e to the x with respect to x, and then integrate 6 times e to the 2x with respect to x. For example 6, we'll integrate 15 sine of x with respect to x, obviously, and then we'll integrate cosine of x minus secant squared of x with respect to x. So let's do all 4 of those. We'll do example 5, e to the x, and 6 e to the 2x. And then the examples on example 6, which are 15x and cosine x minus secant squared x. Okay, so let's do these 4. Again, if you want to try this on your own, you can push pause, try it on your own, and come back. But I'm going to go right into it. We integrate e to the x, and we get back an e to the x, and then obviously we have to tack on our plus c. So you integrate e to the x, you get back e to the x plus c. That's everybody's favorite thing to take a derivative of or integrate because it gives you back itself. Now, if we have e to the power 2x and we want to integrate that, then I'm still going to get e to the 2x, but then I have to go and divide the coefficient by 2. So in this case, my coefficient starts as 6. When I divide by 2, I get 3. So I get e to the 2x times coefficient of 3. And then obviously I have to tack on the plus c at the end. So 3 e to the 2x plus c would be my final answer there. If we're integrating 15 times sine of x, well, the coefficient of 15 just stays out front. And then when you integrate sine, you get a negative sine of x with respect to x. You get a negative cosine. So what's going to happen is we're going to get negative 15 times cosine of x plus a constant of c. So again, the antiderivative of sine is negative cosine. People often get the negatives and positives with those mixed up because the derivative of sine is positive cosine, but the antiderivative of sine is negative cosine. When I take an antiderivative of cosine of x minus secant squared of x, I'm going to do this separately. Antiderivative of cosine of x is a positive sine of x. Again, this is all with respect to x. Secant squared Well, if you remember, secant squared is the derivative of tangent. So if I have a minus secant squared, the antiderivative will be negative tangent of x. And then obviously I have to tack on a plus c to the end of all of it. So antiderivative of cosine gives you sine. Antiderivative of secant squared gives you tangent. And therefore my final answer is sine of x minus tangent of x plus c. So these are the rules, or these are the basic rules for trig integration. We'll see some more complex rules later for trig integration. Here are the basic rules for this exponential function, e to some power. And then we have, basic rules for things like polynomials, things like rational functions when I can simplify them. Again, we'll look at some more complex integration later on in this unit. But these are the basics. And like I said, hopefully this is review for you. Now, the last thing I want to cover in this video is finding the antiderivative. And by the antiderivative, I mean, can we find a specific antiderivative if I want to integrate a function and I also know some initial condition for that function? And basically what we're going to do is we're going to do the integration, and then I'm going to plug in some initial condition or some initial value to find the constant. So I just basically need to find the specific c that I'm looking for. And I can do that if I know some value that the function passes through, some point that the function passes through. So we'll only do a couple of examples. Let's find the antiderivative of lowercase f of x equals 6x squared plus 8 if I know the antiderivative goes through the point 2 comma 17. And then let's do the same thing. Find the antiderivative of lowercase f of x equals 6x squared plus 8 if I know the antiderivative, instead of going through the point 217, now goes through the point 248. So the antiderivative of this function we can find by integrating. That will give me a plus c at the end when I integrate this. And then to find the plus c, what the actual value of c is, all I need to do is plug in a point. Okay, so we start out by integrating 6x squared plus 8. And obviously we integrate that with respect to x. Using the rules we have gone through earlier, that's going to be x to the third. Divide by 3, you get 6 over 3 is 2. So 2x to the third plus 8x plus some constant. So that is our antiderivative. I'm going to call that capital F of x. So my antiderivative is 2x to the third plus 8x plus c. Now I also know that the antiderivative goes through the point 2 comma 17. What that means is When I plug in 2 into the x, I get an output that is 17. In other words, this capital F of 2 is going to give me 17. So that's what I do. I say, well, the output is going to be 17 when I plug in a 2. So I plug in a 2 for x, and I get out a 17. And this is going to give me an equation that I can easily solve for c. So 2 times 2 to the third plus 8 times 2. On the right-hand side, that's 32. So I get 17 is equal to 32 plus c. And basically, that means c is negative 15. All right, just subtract 32 from both sides. So what I get is that my final answer, because it asked me for the actual antiderivative, is that the antiderivative that I'm looking for, the one that's going through the point 217, is actually the antiderivative capital F of x is equal to 2x to the third plus 8x minus 15, or plus negative 15. And so that's the specific antiderivative that I want. Now, all of this would basically be repeated, at least the first part of this would be repeated for this next question. The next question says, what if instead of going through the point 217, what if my antiderivative was actually supposed to go through the point 248? Well, again, that means if the antiderivative is called capital F of x equals 2x to the third plus 8x plus c, I know that capital F of 2 has to give me out 48. And so 48 is what I get when I plug in 2. Again, that's 2 times 2 to the third plus 8 times 2 plus c is equal to 48. In the exact same way I did up here, I solve for c. So in this case, I'm gonna keep it on the same page there. In this case, I'm gonna get 48 is equal to 32 plus c. And when you take 48 minus 32, you get 16. So c is 16 in this case. And that means that my actual antiderivative, the one that I'm looking for in this case, is 2x to the third plus 8x plus 16. And that's it. That's the whole thing. So if you want to find specific antiderivatives, you can simply integrate. And then if you know some additional information about the antiderivative, like a point that it goes through, you can simply plug in the point and find the specific value for C in that instance. And again, notice that going through the point 217 gave me this antiderivative, 2x to the third plus 8x minus 15, whereas going through the point 248 gave me a different antiderivative. 2x to the third plus 8x plus 16. Now, we don't do this a whole lot in our class. We don't find specific antiderivatives. It's much more common to just calculate the integral and get the entire class of antiderivatives. So we do that a little bit more than finding specific antiderivatives in this class. But you can find specific antiderivatives using this technique. So that is all for this section. Remember that the rules for integration, those are the ones that are going to be very important to remember. You should be very fluent in these rules for integration, these basic rules for integration as we move forward. We're going to use those a lot in this unit. So the standard trig integration rules, the e to a power rules, e to the ax rules, and the x to a power rules, along with dealing with, constants and being able to break up terms and integrate both things. So hopefully, again, most of that is review, and that is the end of this section.